Every message you send, every video you watch, every photo you take, every song you stream, and every game you play is built from only two symbols, 0 and 1. Not words, not colors, not sounds, not images, just patterns of zeros and ones. At first, that sounds almost impossible. A sunset has millions of colors, a voice has rhythm, tone, emotion, and tiny vibrations in the air. A movie contains movement, music, light, shadow, faces, places, and entire worlds. But underneath all of it, the computer only sees a long sequence of tiny choices. Off or on, low voltage or high voltage, no signal or signal, 0 or 1. So here's the question. Why did the digital world choose something so simple? And what would happen if computers stopped using binary? To understand that, imagine you are building a city where every message must travel through millions of tiny gates. Each gate has to make a decision. Should the signal pass through, or should it stop? Should the next path open or stay closed? Now imagine those gates are not made of stone or metal. They are microscopic switches inside a computer chip. These switches are called transistors. A modern processor can contain billions of them. Each transistor is incredibly small, but its job is simple. It controls the flow of electricity. In the simplest way, it can act like a switch, off or on. This is one reason binary became so powerful. Computers are physical machines. They are not floating in a perfect mathematical world. They exist inside reality, where electricity is noisy, heat exists, materials are imperfect, and tiny signals can be disturbed. If you want to build a reliable machine, you do not want each switch to carefully distinguish between 20 different meanings. You want the switch to answer a simpler question. Is the signal low or is it high? Is it closer to 0 or closer to 1? This simplicity makes computers reliable. Think of it like a light switch in a dark room. If the switch is clearly down, the light is off. If the switch is clearly up, the light is on. There is no confusion. But now imagine a strange light switch with 10 positions. Position 0 means darkness. Position 1 means very dim. Position 2 means slightly brighter. Position 3 means brighter again, and so on. In theory, that switch could store more information. But in practice, it becomes easier to make mistakes. If the switch is slightly bumped, was it on position 6 or 7? If the room vibrates, if the switch wears down, if the labels fade, the system becomes harder to trust. Binary avoids that problem by making the difference large and clear. 0 and 1 are far apart. That distance creates safety, and that safety is the foundation of the digital world. Now let's do a thought experiment. Imagine you want to send a secret message across a mountain at night. You and your friend only have one lamp. You agree on a simple code. Lamp off means 0. Lamp on means 1. With enough flashes, you can send any message. At first, that sounds slow. One lamp, only two symbols. But if you create patterns, the possibilities grow quickly. One flash can represent 2 possibilities. 2 flashes can represent 4 possibilities. 3 flashes can represent 8. 8 flashes can represent 256 different patterns. That is already enough to represent letters, numbers, symbols, and instructions. This is the hidden power of binary. Each individual choice is simple, but many simple choices together create enormous complexity. A single bit is tiny. 8 bits become a byte. Thousands of bytes become text. Millions of bytes become images. Billions of bytes become videos, games, software, and entire operating systems. The magic is not in the 0 or the 1 by itself. The magic is in the pattern. A computer does not understand the letter A the way a human does. It does not see it as a shape, a sound, or a meaning. It stores it as a number. That number can be represented in binary. The same idea applies to everything else. A color can be represented by numbers. A sound can be represented by measurements. A photo can be represented as a grid of pixels, where each pixel has numerical values for color and brightness. A video is many images shown quickly combined with sound, timing, compression, and instructions. So when people say that computers only understand zeros and ones, they do not mean computers are stupid. They mean computers are built on a language of incredibly simple physical states. And from those simple states, we create layers of meaning. This is important because it explains why binary is not just a random choice. Binary works because it matches the physical world of electronic switches. It is easy to build, easy to detect, easy to correct, and extremely reliable at massive scale. A computer is not powerful because one transistor is smart. A computer is powerful because billions of simple switches can work together at incredible speed. That is the first key idea. The digital world is complex on the surface, but underneath, it is built from simple, reliable decisions, 0 or 1, off or on, false or true. And once you understand that, the next question becomes even more interesting. If binary is so useful, why would anyone ever want something else? Imagine you are designing a new kind of computer. You look at binary and think, why only 2 symbols? Why not use 0, 1, 2, and 3? Or 10 different states? Or 100? Wouldn't that store more information in the same space? At first, the idea makes sense. Humans use 10 digits every day. We count with 0 through 9, so why don't computers do the same? The answer is not that it is impossible. The answer is that it is harder to make reliable. Let's return to the mountain lamp. With a simple binary lamp, off means 0 and on means 1. Even if the light is a little weak, your friend can probably still tell whether it is off or on. But now imagine the lamp has 10 brightness levels. Level 0 means no light, level 1 is barely visible, level 2 is a little brighter, level 3 is brighter again all the way up to level 9. In perfect conditions, this might work. But real conditions are never perfect. Fog rolls in, the air moves, your friend gets tired, the lamp battery weakens, the distance changes. Suddenly, level 5 looks like level 6. Level 2 looks like level 3. Messages become uncertain. That is the problem with using many states. The more meanings you pack into one signal, the harder it becomes to distinguish them under noise. Computers face a similar problem. Inside a chip, signals are not perfect. There is electrical noise, there is heat, there are tiny variations in manufacturing. There are limits to how precisely voltages can be detected, especially when billions of operations are happening every second. Binary gives engineers a huge advantage. You do not need to measure the exact value perfectly. You only need to decide whether the signal belongs on the low side or the high side. That makes binary forgiving. If 0 is represented by a low voltage and 1 is represented by a high voltage, then small errors may not matter. A slightly imperfect 0 is still treated as 0. A slightly imperfect 1 is still treated as 1. This is one reason digital systems can copy information without slowly degrading. Think about an old cassette tape. If you copy a tape and then copy the copy and then copy that copy, the quality gets worse. Noise builds up. The signal degrades. Digital information is different. If the system can still tell zeros from ones, it can rebuild the pattern cleanly. It can copy the information again and again without the same kind of gradual decay. That is one of the greatest strengths of digital technology. It turns messy physical signals into clean logical symbols. Now let's do another thought experiment. Imagine a library where every book is written using only 2 words, yes and no. At first, this sounds absurd. How could 2 words contain a novel, a law book, a song, or a scientific paper? But then you realize each page is not meant to be read as normal language. The words are arranged as code. Every group of yes and no answers points to a letter, a color, a sound, an instruction, or a location. The system is strange, but it is powerful because it is exact. If one page says yes, no, no, yes, yes, no, that pattern always means the same thing inside the agreed code. That is how computers build meaning. They do not need many basic symbols. They need reliable rules for combining simple symbols. This is why binary dominates modern computing. But binary is not the only possible way to compute. Some experimental systems use more than two states. Some memory technologies store multiple levels inside one cell. Analog computers can work with continuous signals rather than discrete zeros and ones. Quantum computers use qubits, which are often described as being beyond ordinary bits. But this is where many explanations become misleading. A quantum computer is not simply a computer that uses 0, 1, and something in between. And a qubit is not just a magical super bit that stores every answer at once. A classical bit has one clear value when used in computation, 0 or 1. A qubit is described by a quantum state. Before measurement, that state is associated with probabilities. When you measure it, you get a classical result, 0 or 1. The power of quantum computing does not come from simply replacing binary with more digits. It comes from quantum effects such as superposition, interference, and entanglement. These effects allow certain algorithms to shape probability patterns in ways classical computers cannot easily copy. But that does not mean quantum computers will replace all normal computers. For most everyday tasks, binary classical computers are already extremely good. Sending messages, editing videos, browsing websites, running games, managing files, streaming music, and processing ordinary business data do not automatically become better just because a quantum computer exists. Quantum computers may be powerful for certain special problems, especially problems involving quantum systems, optimization, or hidden mathematical structure. But the normal digital world will not simply throw away zeros and ones. There is another reason. The entire internet, almost every app, every operating system, every database, every processor, every storage device, and almost every programming language is built around binary foundations. Changing that would not be like changing a keyboard layout. It would be like rebuilding the roads, engines, traffic lights, maps, fuel systems, and rules of transportation for the entire planet. Binary is not just a technical choice. It is an ecosystem. And ecosystems do not disappear overnight when a new idea arrives. So if computers stopped using 0 and 1, the change would not be simple. It would affect hardware, software, memory, communication, storage, security, and the way information is represented. The more you think about it, the more binary starts to look less like a limitation and more like a brilliant compromise. Simple enough to be reliable, flexible enough to represent anything, physical enough to build, mathematical enough to scale. That is why two symbols changed the world. Now imagine a final thought experiment. You are standing inside a giant machine the size of a city. Every building is a processor. Every street is a wire. Every traffic light is a transistor. Every person moving through the city carries a tiny message. But the entire city obeys one simple rule. At every intersection, the message must choose between two paths, left or right, stop or go, 0 or 1. No single choice looks impressive, but when billions of choices happen together, patterns emerge, a photo appears, a voice is reconstructed, a payment is verified, a video loads, a game world reacts, a message crosses the planet. This is what makes computing so fascinating. The machine does not begin with meaning. It begins with switches. Meaning is built in layers. At the lowest layer, there are physical signals. Above that, bits. Above that, numbers. Above that, text, images, sounds, files, programs, networks, and interfaces. By the time the information reaches you, it no longer feels like electricity. It feels like a face on a screen, a song in your headphones, a message from a friend, or a world inside a game. But underneath, the city is still making tiny binary decisions. This is also why computer errors can be so strange. If one bit flips in the wrong place, the effect can be invisible, or it can corrupt a file, or crash a program, or change a color, or break an instruction. The meaning depends on where the bit lives inside the larger pattern. A 0 is not important by itself. A 1 is not important by itself. Context gives the bit its power. This is similar to language. A single letter may not mean much alone, but change one letter in the right word, and the meaning changes completely. Change one number in a bank transfer, and the result can be serious. Digital systems are built from tiny pieces, but those pieces are arranged with extreme precision. That precision is what makes software possible. When a programmer writes code, they are not usually writing zeros and ones directly. They write in a human-readable programming language. But that code is eventually translated into instructions the machine can execute. Those instructions are represented in binary. So even the most beautiful app, the most advanced artificial intelligence model, and the most complex simulation eventually depend on patterns of bits moving through physical hardware. This gives us a different way to see computers. A computer is not a brain in the human sense. It does not understand the world the way we do. It manipulates symbols according to rules. Those symbols can represent almost anything if we create the right encoding. That is why binary is so powerful. It separates the physical machine from the meaning we build on top of it. The same 0 and 1 can represent a letter, a color, a sound, a command, a password, a pixel, or part of a neural network. The symbol is simple. The interpretation is everything. So what would happen if computers stopped using 0 and 1? The honest answer is, most computers probably will not. At least not in the way people imagine. Binary is too useful, too reliable, and too deeply connected to how electronic hardware works. Future machines may add new layers. Quantum processors may help solve certain specialized problems. Neuromorphic chips may imitate some features of biological nervous systems. Analog systems may return for specific tasks. Memory devices may store multiple levels in clever ways. But the binary computer will remain one of the greatest inventions in human history. Not because it is complicated, because it made complexity possible. It turned electricity into logic, logic into numbers, numbers into language, language into software, software into the digital world. And that digital world now surrounds us so completely that we barely notice the miracle anymore. We tap a screen, and a message crosses oceans. We take a photo, and light becomes data. We speak into a microphone, and air pressure becomes numbers. We stream a movie, and millions of tiny measurements become motion, color, and sound. All of it depends on the same quiet foundation. 0 and 1, off and on. A choice so simple that it almost seems too small to matter. But repeated billions of times. At incredible speed. With incredible precision, it becomes something enormous. It becomes the internet. It becomes artificial intelligence. It becomes modern science. It becomes global communication. It becomes the hidden language of the age. So maybe the real question is not why computers use 0 and 1. Maybe the real question is how something so small became powerful enough to build a world. Because every digital thing you have ever touched, every file you have saved, every video you have watched, every message you have sent, and every program you have opened is part of one enormous pattern. A pattern made from only two symbols. 0 and 1.